My name is Yudo. I'm a solutions architect here at Amazon Web Services with area of that in machine learning. And we are so glad to have you joining us today for this AWS Summit Online. This particular session, what machine learning can tell from your software development history, is about using machine learning to do code search and other things for improving your software development process, and how to run it on Amazon Elastic Kubernetes Service or EKS. Quote AI will join me in this presentation to share their expertise in this field and to share their machine learning journey in EKS. We will have Dr. Mikhail, who is the chief scientist and co-founder of Quote AI, and Corvin, who is the lead data scientist. I hope that by end of the session, we will learn these points. Firstly, how we can utilize machine learning to improve our software development process, how Quote AI can provide a solution for this. We will also see how Quote AI runs its machine learning infrastructure on AWS, especially in EKS. Then we will see Quote AI's journey in scaling their architecture, followed with a demo. Finally, we will see the Kubernetes ecosystem that EKS integrates with and what offerings are there. Let me first introduce you to Quote AI. If you're a developer yourself, or if you are running a development team, you may contemplate at one point thinking that, wouldn't it be nice if I can do an intelligent search on my code base, find the relevant code chunk, and figure out who I can approach to get more information on the code chunk. We call this your AI assistant on code. And this is what Quote AI provides. Let me pass it on to Dr. Mikhail, who will take you deeper into the technology. Corvin will then share the architecture on Amazon EKS. Go ahead, Dr. Mikhail.
Thank you, Yuda. So what if I tell you that your company has a treasure full of data which can help with answering both technical and business questions? Almost every company in the world nowadays has to be an IT company, at least partially. And the dataset, which we all have in Git, is fantastically rich. It doesn't just contain code, but also documentation, discussions, and metadata, which can tell a story of the codes and the whole project's evolution. Who is the best person to talk to about the new feature or a problem? Why did we implement the solution that way? This and many other questions could be answered straight from your code base. And if you think that these questions are not critical and it's just nice to have the answers to them, let me ask you a question. How much time do you think software engineers spend on code? According to the studies from Microsoft, Stripe, and SMU, software engineers spend from 5 to 28% of their time coding. Big contributors are code comprehension, reading code and documentation, and navigation through code. Engineers waste 13 hours per week on technical debt and 17 hours per week on code maintenance, inefficient code, errors, and debugging. Together, it almost results in 4 working days. And with COVID, the situation only became worse. Although developers started to work from home and the numbers of their working hours increased, the productivity didn't go up, which you can see from this graph from the study completed just 2 months ago. 73% of technologists were reporting burnout at the end of April, far above from 61% who felt burned out in mid-February. Developer activity, including pushes, pull requests, reviewed pull requests, and commented issues per user, increased slightly year over year. This suggests that developers have continued to contribute and their workflows have remained resilient during the crisis. Patterns of activity have implications for burnout. During the transition to new work routines, developers' activity may be sustained through more time being spent online. If additional work is happening at the expense of personal time and breaks the replenish and maintain healthy separation, the trade-off may not be sustainable in the long run. With all these problems and challenges on one hand and vast untapped data on another, imagine how great it would be if we could have all those lines, patterns, all different ways to solve the problems in our mind while writing the code. Well, not all of them, but only a good part of it. So what can machine learning do with code right now and how? Well, machine learning on code is related to NLP programming language structure, and social and historical analysis, such as a contribution graphs and commit time series. It aims to learn from large-scale source code datasets in order to automatically perform software engineering tasks such as code completion, code optimization, assisted code reviews, documentation generation, etc. So for code completion, which is auto-completion and intelligent code completion, it speeds up software development because you don't have to memorize the names, nor types of the whole name. Even more importantly, it prevents error coming from typos and confused names. Finally, it also allows for less reference to external documentation as interactive documentation on many symbols in an active scope appears dynamically in the form of tooltips while coding. There are many tools out there coming from companies like IntelliJ, Kite, and Codota, and often code completion doesn't use machine learning. It works by using a thematically generated in-memory database of classes, variable names, and other constructs that the application being edited defines of references. On this screenshot from tab 9, you can see a smart example of how useful a sensitive code completion tool can be. Just one letter of difference, get users instead of get user, changes the suggested input. Code optimization is a bit of a vague term and is often used to address a program transformation technique, which tries to improve the code by making it consume less resources and deliver high speed. Some ways to get there are through replacing high-level general programming constructs by very efficient low-level programming codes. However, often the change in habits can help much more. Clarity and style, coding efficiency, test effectiveness, profiling, and machine learning can help with some of this. Automated code review is a classic code review. It's developer systematic check on others' code for mistakes, and it has been repeatedly shown to accelerate and streamline the process of software development like few other practices can. Its only problem, it is very time-consuming. No wonder that many studies have been done on this topic, and a few companies are working on assisted code review tools. CodeGuru is a machine learning-based service that offers two functionalities, reviewer and a profiler, as shown here in the different stages of a CI/CD developer workflow. In a nutshell, reviewer runs automated code reviews and carries out steady code analysis tool providing recommendations, whereas profiler evaluates the dynamic app performance in runtime and provides you with the recommendations. These recommendations are generated using machine learning models that have been trained from millions of code reviews and tens of thousands of application profiles conducted within Amazon as well as open source projects. Automatic bug detection and bug fixing have been a holy grail for many years. Typically, the goal of such techniques is to automatically generate correct patches to eliminate bugs in software programs without causing software regression. Although the problem is vast and most probably cannot be addressed by just one solution, some studies show very interesting and promising results. For example, DeepBugs, a deep learning approach to name-based bug detection, yields bug detectors which can have a very high accuracy between 89 and 95%, which are quite efficient, less than 20 milliseconds per analyzed file, and reveal more than 100 programming mistakes within 68% true positive rate in a real-world code. Finally, documentation generation. Ask any developer whether they like to write documentation, and I'm sure you won't get a positive answer. Even less so will like updating the documentation, which result in semantic voids, interruption errors, and growth of tech debt. Until very recently, this area was largely untapped because most problems in this area are unsupervised or at most weakly supervised. It was, and still is, quite costly to manually label dataset, so researchers typically have to develop correlated heuristics. We developed a set of models that allow us to generate documentation straight from the code and keep it always up to date. So what can you learn from your code with Quad AI? Apart from documentation generation, Quad also helps you with one of the problems pointed out in the different studies in the beginning of the presentation. Engineers spend almost a quarter of their time on code navigation. So how do they do it now, and is there a better way to find context? There are roughly two groups of solutions which software engineers are using right now. The first one is classic documentation platforms like Wiki, Confluence, which have decent discoverability, but require a lot of time to be filled and updated. The second one is the communication channels like Slack and Zoom, which are fast and help to sync quickly, but it is almost impossible to rediscover the information afterwards. Our platform, on one hand, automatically generates the content and keeps it up to date, and on another one, allows you to discover the content fast with search, filters, and intelligent suggestions. When you submit your repository to QuadAI, it breaks every file into code snippet, and for every snippet, generates documentation on which you can search. For example, here we see the results on the search query. All content here, except for original code, is automatically generated. So questions like where do I upload video or where is the function called when the upload is done are generated straight from the code, as well as the semantic tags, which you can see, and many others like cloud storage operation, bucket upload, and video. They're supposed to summarize the code as well as provide a way to discover and group content. On the left side, you can see a panel which allows you to filter search results and to use the semantic tags. We generate two types of tags: technical, like HTTP API, MongoDB query, and Redis, and also business-related ones, like user, video, upload. You can also work on code in a browser mode, which should be very intuitive for software engineers. In it, you can have a file tree on the left side, code in the center, and generated content on the right. Apart from questions and semantic tags, we provide more context on each snippet of code. For example, who are the experts on this code? Experts are basically developers who might want to talk to if you plan to use or change the code and need deeper understanding. We look at the contributions on the file and snippet levels, commit, and how often one's code is using similar technologies or business problems. If you want to have even more context, you can take a look at the related snippets of code suggested by our engine. They might help you to understand the code base better and quickly identify next steps. As you just saw, most of the intelligence generation and context discovery in our platform is coming either from code or from text in natural language. Natural language processing has been an extremely popular part of machine learning recently. But what about machine learning on code? How different is code from text? And what can we reuse from NLP? Although there are many similarities between programming code and text in natural language, there are also three main differences. Code is almost every language has a more regular structure than a text, which helps to avoid relearning those regularities. 2, code syntax allows not to relearn structures of standard grammatical constructs. Finally, code semantics allows not to relearn the semantic role of variables, scoping rules, and others. However, there is no silver bullet when it comes to semantic representations of code. Every representation of code comes with a trade-off. Wherever we are trying to capture the functionality and the meaning of code, we have to balance learning effort, which is a amount of training time and data, and analysis effort, semantic depth. In two extreme scenarios, we have code representations which are language agnostic, which require a lot of work, and a language or task specific, which require less work. Let me now pass it to Corwin, who will tell you more about architectural level.
Thank you, Mikhail. Coming back to the UI of QuadAI, you'll find many elements that contain intelligence: question titles, tags, expert information, snippet revision history, and so on. All these features are created by infrastructure that we built on AWS. Let me give you an overview of the current state of our architecture and the learnings we gained along the way. Naturally, everything starts with your source code. We currently support GitLab, GitHub, and Bitbucket. From there, our data pipelines retrieve your source code and split it into code snippets. On these snippets, we apply several layers of code intelligence. Some parts of the code intelligence are generated inside of the pipeline. Other parts are served through a network of data science models and services. All the services are accessible through an internal load balancer and are deployed as Docker containers that are pulled from the Elastic Container Registry. As the last step of our pipeline, we sync the code and intelligence into 3 storage backends. With Elasticsearch, we store data in a searchable format that empowers our code search engine. Neo4j stores aspects of your code as a knowledge graph and allows us to extract hidden insights how your code developed. Finally, AWS RDS stores large parts of the data, which you will see on the UI. From there, our API server and web app access the data and the code intelligence that you see in the UI. This is the only point where data leaves our VPC network. All of this is deployed inside of an auto-scaling Kubernetes cluster managed by EKS. On top of EKS, we use a number of frameworks for observability, scaling, and error monitoring. In the process of setting up Kubernetes, EKS facilitated the setup of large parts of the infrastructure by a lot, by managing Kubernetes control plane, cluster auto-scaling, security settings, and many other aspects out of the box. Of course, we did not start with this architecture as is. It developed over time, and we certainly haven't reached the end. I want to share 3 major learnings and how it shaped our philosophy so far. Think business function first. A model should fulfill an end-to-end business function. The input is exactly what the model users have, and the output is what they need. An example from our case, the input is the raw, unprocessed code, and the output is the code description. That comes with 3 major advantages. First, it keeps you and your team on track, what the model ultimately has to deliver. Second, it makes the model integration easy and reduces friction among model users and data scientists. And third, data scientists have the autonomy from the raw data to the final result. As you've heard from Mikhail, there is no silver bullet to code processing. So the processing is just as much part of the model development as the model itself. If we made the user implement the pre-processing, we would lose this flexibility. Let me give you an example of how we generate code descriptions. Our data pipeline calls an API, sends the source code, and gets the code description back. The model deployment itself takes care of the correct pre-processing, model inference, and post-processing, end-to-end. Across all our models, we use a unified and configurable schema for API requests and response that is easy to use and to remember. A single business function can get a lot more complicated than that. To generate our tags, we use a composition of various models. These models use multiple downstream services, such as TensorFlow Serving, code parsers, or even Elasticsearch. Although these submodels are available standalone, we have a compound model that combines them, again, end-to-end. Secondly, minimize the engineering effort for data scientists. For every model deployment, there are 2 major work packages, the engineering and the data science. The engineering is the part that makes the model usable while ensuring that it's efficient, scalable, observable, and fault-tolerant. The data science is the core of what the model does. It defines the pre-processing, the inference, and the post-processing. It's the bread and butter of the data science work. As you can imagine, the engineering part is a good bit of work, but it's also uniform across all model deployments, while the data science is always different. In QuadAI, we invested some time to segregate these 2 areas by standardizing the engineering part and the code structure. For all model deployments, we have a boilerplate app and utilities that meet all engineering requirements. For the model, then we slot in the 3 steps pre-processing, inference, and post-processing for a first minimal version. After that, we can extract with custom request validation and deployment configuration fast and easy. This not only reduces the time to deployment, but it makes our code base much more maintainable and understandable. Thirdly, iterate on your tooling whenever you hit limitations. Our current architecture developed over time, And we started with the KISS principle. Keep it simple and stupid. In the beginning, our few models were directly deployed onto compute instances, using Flask as a microservice framework to serve them as an HTTP API. It was cheap, fast, and easy. The first ceiling we hit, it was difficult to move deployments to other instances. We also faced service outages when a service had died and we had to manually restart it. Operating all models in Docker containers solved these limitations. The containers are easy to port and restart automatically after a failure. With the number of models growing, we hit the problem that each TensorFlow model would require its own GPU instance. To make this even more expensive, we faced low GPU utilization as the CPU and GPU resources were tightly coupled, and the pre-processing was slower than the inference. That was solved by introducing TensorFlow Serving. This decoupled CPU processing and GPU inference and made it possible to serve multiple models on a single GPU, faster and cheaper. With rising model requests, we naturally faced scaling issues, as we still served all models on a single GPU instance that just did not scale. In addition, the number of models grew further without any standardization and formalization. This not only made it harder to maintain and connect them, but also, again, increased the idle cost. You may have anticipated the next logical step, Kubernetes. To manage the rising number of models, we introduced standards around code structure, environment variables, service names, and so on, and moved all deployments to Kubernetes. Although Kubernetes made a lot of things easier, cheaper, and more scalable, it also opened the door to more services and more complicated service networks. With these high numbers of services, often running idle, we again faced low resource utilization and high cost. Another ceiling we hit, debugging service bottlenecks and bugs in downstream services. With naked Kubernetes, it was very hard to find reasons for bottlenecks and bugs that are buried in the core graph. That led us ultimately to the infrastructure we have now. With the introduction of Knative, the majority of our services now scale down to 0 in idle times. In addition, the service mesh layer Istio enables a lot of tooling that gives us introspection into potential bottlenecks and issues in the service graph. Let me give you a quick demonstration how we currently run our models and our services. I'll start with one of our model APIs and how Knative helps to save idle costs in operation. On the left side, you see Jupyter Notebook, from where I will send the request to our model. On the right side, you see a terminal with all the services that are currently running inside of our Kubernetes cluster. For this snippet that fetches a user by ID, I want to generate the code description. This is our request schema, which contains a configuration as well as a batch of snippets for which I want to run inference. Once I execute the model request, you see that on the right side, the model immediately comes up. After some time for a cold start, for initializing the Kubernetes container, as well as starting up the deployment application, we finally get the model result. As you can see, this is get user by ID. If I now execute this command again, then you will see that it's much faster since there is no more cold start. Let's move on to the service monitoring. I generated some load on our demo cluster. And looking at the same terminal now, you can see there are a lot more elements that are operating. This is the Kubernetes cluster auto-scaling on demand. I'd like to give you a quick peek into two of our systems, Kiali and Grafana. This is Kiali. We use it to identify bottlenecks inside of our service network and visually investigate the services. As you may have noticed, this is the same service network that I showed you earlier in one of the slides. External requests are coming in, both to generate code descriptions from one model and to generate tags from a compound of 3 different models. On this high level, you get a quick overview of what's the 95th percentile of the response times written directly on the arrows. The arrow color indicates if there is an error rate or not. On this high-level overview, you quickly get a sense where latencies and error rates come from. For example, for tag generation, we can see that the error rate originates from this model TF2. From here, we can now dig deeper and try to understand where does the problem come from and solve it. Let's now have a look at Grafana, where we monitor a broader set of characteristics for each of our deployments. On this dashboard, we see a rich summary of metrics. It gives us insights into how much memory we are consuming, how much CPU we are utilizing, as well as how much our service had scaled over the past. We also get insights about request characteristics, such as request error rates and request response times, for both incoming and outgoing requests. In addition, we also use Grafana Loki to integrate the logs from the deployment directly into the dashboard. This helps us to investigate the processing times even further and go down to details without having to switch our tooling. Now let me show you one more dashboard that we use to monitor our inference servers. This is the TensorFlow serving dashboard. This is very similar to the previous one, with a slight difference. There is also the GPU utilization on the inference servers. So here you can see that over time, our cluster had scaled up the number of inference servers from 0 to ultimately 3. This GPU scaling is empowered by EKS and the horizontal pod autoscaler that scales the replicas based on the GPU duty cycle metric that is provided by the monitoring system Prometheus. Udo will now give you some more detailed information on EKS and adjacent services that you can utilize to run your workloads on the cloud.
Thank you, Corvin. Now that we have seen how Quote AI runs its machine learning infrastructure in EKS, let's see how anyone may bring its Kubernetes infrastructure to AWS too. We recognize that our customers might not be starting from scratch when they build on AWS Container Services. They may have chosen Kubernetes as their core and have existing tooling around it. EKS gives you the ability to bring the services you want and build in a flexible environment. Of course, if you want to use EKS with all of the AWS services, you can do that too. For example, in this diagram, you can choose to use Istio for the service mesh in Amazon EKS, just like how Quote AI did. Alternatively, you can also use AWS App Mesh, which is a service mesh offering. Another example, you can use Prometheus and Grafana and self-manage them. Alternatively, you can use both tools, which are managed by AWS, called Amazon Managed Service for Prometheus and Amazon Managed Service for Grafana, both in preview. Amazon EKS manages how your containers run, but you still need a compute layer. There are multiple options for where that happens. You can choose the right tool for the right job to get the right blend of cost, performance, and features. If you only care about containers and scale on container level using Kubernetes Horizontal Pod Autoscaler or HPA, you may be interested with Fargate. Fargate allows you to run serverless container where AWS will handle its scalability on the compute infrastructure layer and pay only for the containers running. You can run your pods on Amazon EC2 as well, which has an option for spot instance that allows for up to 90% discount on the compute cost. You can check our documentation on how to host a fault-tolerant workload on Amazon EKS with spot instance and benefit from its cost savings. If you need to run Kubernetes managed containers on premises with a consistent hybrid experience with the cloud, you can use AWS Outposts. This is especially if you require local data processing or local residency. AWS Local Zones is an extension of an AWS region, suited for customers who need the ability to place resources in multiple locations closer to the end users. AWS Wavelength is an ultra-low latency mobile edge computing suited for 5G applications, interactive and immersive experiences, and connected vehicles. And coming soon, you can run EKS on your own managed infrastructure with EKS Anywhere and EKS Distro. This is about how you can run Kubernetes on AWS. There is another customer story who ran their machine learning platform on Amazon EKS. iRobot runs Kubeflow on Amazon EKS, which integrates seamlessly with AWS, allowing rapid experimentation with access to GPU instances. You join the AWS Summit to learn, and you can keep on learning after the summit with resources from AWS training and certifications. We offer over 65 courses, many available free and on demand, as well as virtual instructor-led training. When you're ready, prepare for the AWS Certified Machine Learning Specialty Exam, which validates your skills. For more information, visit https://aws.training/machine learning, and be sure to check out our AWS Ramp-Up Guide to learn more. Here, we come to the end of our presentation. We have seen how machine learning can be used to improve our software development process. We have learned how Quote AI improved their architecture over time. And we have also learned how they run their machine learning process on Amazon EKS. I would like to extend my special thanks to Dr. Mikhail and Corwin from Quote AI. Thank you to all of you for attending this session. I hope this is useful, and please complete the survey for the session. Thank you.